this video, we are going to review what we have discussed regarding mathematical induction, and we will actually talk about what mathematical induction is. As you may have noticed, mathematical induction is a complex proof structure, and you will need to practice several different examples to get the hang of it. To be honest, it would be cruel and unusual to expect you to understand mathematical induction at this point because of the fact that we have only done one example over the course of a few videos. You really do need to do at least 10 examples to get the hang of mathematical induction because it is a proof technique that you never encounter in common philosophical arguments. Basically, what I'm trying to say is that mathematical induction is like learning how to ride a bike. When you learn to ride a bike, typically you're a kid, and bikes are, one, something you've probably never seen before, and two, bikes are hard to learn. At least when we discuss sequences, those mathematical objects are things that you've at least seen before in the past. And so there's not much pressure for me to teach that with the extent of teaching that mathematical induction demands. So in order for me to treat my students fairly here, I should definitely spend several videos focusing on mathematical induction. Hey everyone, real quick, I just want to mention that this video is a part of a whole course that I made. You can find a link to this entire course in the description below and make sure to click on that subscribe button. Up to this point, I've used mathematical induction loosely. I've never really defined mathematical induction. If I were to ask you, what is mathematical induction? You'd probably pause, and rightfully so, even though we've gone through a few lectures and an example involving mathematical induction. That's not your fault though. If you're lost, that's totally normal. That's because mathematical induction is not something to just shove in your face. If you're teaching a kid to ride a bike for the first time, you don't just throw them a bike and say, good luck. That being said though, since I've slowly introduced this concept of mathematical induction at this point, I feel that it is fair to show you what mathematical induction is. So without further ado, this is the definition. Start by saying what the statement is that you want to prove. Let P of n be the statement blank. To prove that P of n is true for all n greater than or equal to 0, you must prove two facts. First is the base case. You have to prove that P of 0 is true. You do this directly, and this is often easy. It's just that part of the proof is like proof by example, but you do it for specifically n equals 0. And we'll talk about special base cases in a moment here. Inductive case, you prove that P of k implies P of k plus 1 for all k greater than or equal to 0. And to do that, you get to assume that P of k is true, and you have to prove that P of k plus 1 is true. That is, you prove that for any k greater than or equal to 0, if P of k is true, then P of k plus 1 is true as well. This is the proof of an if-then statement, so you can assume P of k is true. P of k is called the inductive hypothesis. You must then explain why P of k plus 1 is also true given that assumption. Assuming you are successful on both parts above, you can conclude, therefore, by the principle of mathematical induction, the statement P of n is true for all n greater than or equal to 0. Sometimes, it's important to note that sometimes the statement P of n will only be true for values of n greater than or equal to 4, for example, or some other value. In such cases, replace all the zeros here with 4s, or the other value, whatever value you're using. The other advantage of formalizing inductive proofs is it allows us to verify that the logic behind this style of argument is valid. Why does induction work? Well, think of a row of dominoes set up standing on their edges. We want to argue that in a minute, all the dominoes will have fallen down. For this to happen, you will need to push the first domino. That is analogous to the base case. It will also have to be that the dominoes are close enough together that when any particular domino falls, it will cause the next domino to fall. That is analogous to the inductive step. If both of these conditions are met, you push the first domino over and each domino will cause the next to fall, then all the dominoes will fall. Induction is powerful. Think how much easier it is to knock over dominoes when you don't have to push over each domino yourself. You just start the chain reaction and then rely on the relative nearness of the dominoes to take care of the rest. Think about our study of sequences. It's easier to find recursive definitions for sequences than closed formulas. Going from one case to the next is easier than going directly to a particular case. That is what is so great about induction. Instead of going directly to the arbitrary case for n, we just need to say how to get from one case to the next. When you are asked to prove a statement by mathematical induction, you should first think about why the statement is true, using inductive reasoning. Explain why induction is the right thing to do, and roughly why the inductive case will work. Then, sit down and write out a careful formal proof using the structure here. Anyways, thanks everyone, and I'll see you in the next video.